Hello there. In this lecture, I'd not really call it as a lecture, but more like a demonstration or a tutorial session where I'll show you how your TEM data is. I'll take a few examples of HR STEM images, HR STEM micrographs, and also some image stacks and show you how to analyze. Now, when you look at the data that is recorded in the microscope, you typically get some images of either a TIFF or any other format such as DM3, or depending on how you're recording using which camera or which software. So if I have a look at how the raw data recorded in STEM mode looks like, here is an example of a STEM micrograph from strontium titanium oxide. And as you can notice here in this particular image, there is some kind of a distortion that you see here. These are actually columns of strontium and there is some sort of a distortion. This is how typically a raw image looks like, and there is some scale bar which is already given here. This is directly exported from the microscope, and this is, you can record the raw data either with the scale bar or without the scale bar. This is not really in a presentable form for a publication. Now, doing good analysis on the data that you get is as good as performing a good experiment on the microscope. There are examples where you end up making quite some errors if you are not very careful in analyzing and interpreting your data. Now, in this particular image, you can see that since the electron beam is rastered and you're scanning from left to right, there is a high possibility that due to the thermal drift of the TEM holder, you can have slight X and Y movements of the specimen, and this leads to this kind of a distortion. And if you see here again, there is some change. So while you're moving the TEM holder or displacing the specimen, especially when you're rastering and recording images, you often get this, or either due to thermal drift, you might end up getting this. There are automatic drift correction programs available in microscopes, and when you have the drift correction on, you might end up getting a slightly different image. I'll just scroll through and see how it looks like. Here is a sort of a drift corrected image, and this box here is the location from which we obtained EDS data. So here is another example of the image without the scale bar, and here is the image with the scale bar. So you get the data exported in different forms. This is how the STEM data typically looks like, and quite often we just copy and paste these and don't even bother to change the scale bars and make it uniform and presentable. Nowadays, there are certain formats and accepted styles for specific journals, and it is important that you maintain uniformity and consistency in how you label your data and how you interpret the data as well. I'll take some very simple examples. So this is an HR STEM micrograph, and there is another software called Digital Micrograph, which is here, and this is how your typical high resolution TEM micrograph looks like. This is from a silicon sample oriented in 110 direction, and what you see here are the silicon atoms, and I'll take examples of these and I'll show you how to do some measurements and how common errors come in while you're doing some measurements on TEM data. And then with the STEM micrograph and also with the EDS maps, let us see how to prepare a simple image that is sort of presentable for a publication. And I'll also show you an example from in-situ movies. You record image stacks, and let us see how you process stacks. Now, processing a single image itself is a task in its own, and processing an image stack can often be quite time consuming. But it is worth the whole thing in the end. And from my limited experience, acquiring good data takes perhaps an effort of a few days in preparing the specimen, and of course all the time you invest in spending on learning the technique on microscope and acquiring the data. It could be eventually just a session on the microscope, but then analyzing the data certainly takes a lot more time. Let us start with a simple analysis on a high resolution TEM micrograph. Now let us say you have a task of measuring the d-spacings of the atomic columns that you see here. Intuitively, the most common way is you can actually do the following. You right click and there is this profile that you can draw, and this is generally the direct method in which you start, and you try to draw a line like this, and typically you can double click this and you give some kind of an integration width, make it 10 pixels for example, and ensure that this is more or less exactly along the line you want to measure, somewhat like this. And then you get some value here, and let us say we have this number here. So let us say I measure the gap between 10 such atomic columns, and let me open Excel file for you, and I'll call this as iteration 1. So let me just note down measured value iteration 1, and so our measured value here is 2.9505 nanometers. And if I want to look at the d-spacing between two planes, it is that is in nanometers. So this is iteration 1. So let me just write like this, and then you can go for another iteration here, and let us say I measure the value across another set of columns like this, and we can start somewhere here, and I get another number like this. This is 2.95 9497, yeah, which is so. As you can see, I'm using a direct measurement tool that you have through digital micrograph, and in one case I used an integration width, and in the other case I've actually not used the integration width, and I measured despacings. And let me just take a few more values like that. So this is at one region, and let me go to another region like this, and so if I start measuring again, it is .9986. So as you can see, I'm getting quite different numbers using the same kind of a line and using a width or not using a width for the line profile here. And usually when you're starting new on the analysis and you're asked to analyze high resolution micrographs like this, it is common that you start doing such an error. And with these kind of hands-on methods where you are only drawing lines randomly and trying to measure the distances, you can often end up getting errors, and these are always there. Significant experimental errors are always there. Now, what is a slightly better way to do measurement on this in a more consistent manner? So what you can do is, we know that there is always Fourier filtering there, and if I apply a Fourier transform on this particular image, so what is interesting to note is the reflections you see here are sort of rotated by 90 degrees. So whatever direction is in this direction here, so if I draw it with a line like this, this would have turned by 90 degrees here, and it is in sort of this direction. So this is something which I showed you when I was discussing about reciprocal lattice in one of the earlier lectures. But what you can do is, when you have such a periodic repetitive pattern and you want to get a slightly better accuracy in measuring the lattice spacings, you can apply a mask here. So you can see that if I click this and I do the following, I actually get a mask, and right across, let me lower the gamma a bit so that this is visible a bit better, and if I click here, Let me zoom in a little bit more so that it is visible. I'm just holding Control and rolling the mouse wheel so that I can zoom in into this region, and I'll use Shift and click on this here so that it is exactly selecting two spots, and it is more or less centered. And I can do the following. I can say apply mask, and if I keep the masked area, and you get information like this, and if I do inverse Fourier transform, I end up getting the despacings in this kind of a direction. Now on this, if I measure by drawing a line like this, and let us say I give an integration width of approximately 100 pixels. The biggest challenge is when you're measuring the despacing in this direction. When I drew a line directly and I was measuring the distance between these peaks, one of the reasons why the error could have come up is you do not know if it is exactly perpendicular to the direction you intend to measure. So now I see that it is more or less perpendicular. I can make it like this, and over here also. Of course, this would also have some inherent errors because you are still doing this manually. And if I get this and I then start measuring the despacing between these, it is it's giving me 3 point, sorry, it is actually, I was checking between .1018. So this gives me a number like this. Now, in such a situation, I can actually measure at various locations as well, and the accuracy in the lattice spacing when I do it through a Fourier transform, applying a mask and then taking an inverse Fourier transform is perhaps more accurate than directly measuring it by drawing some lines. So there is of course a problem in such high resolution images if they are typically not from a corrected microscope. You have delocalization problem, and when I'm applying a mask like this and I'm measuring the planes here, you would certainly have some kind of a delocalization effect, and there would be some slight shifts or spread here. But nonetheless, you can try this kind of a methodology on various regions within the specimen, and you can average it out statistically, and you'll be able to get in a more reproducible or a consistent manner the average despacing. Now, one of the things that you see is when you're synthesizing a new compound or you have a new phase or something, the common way in which most of us try to correlate the lattice spacings is get X-ray diffraction data, approximately get some value of the lattice spacing, and you just try to look around in which of the directions is it matching, and then you somehow try to course correct or fit the data. That is not the actual way, but rather do a more systematic estimate and measure the lattice spacings in such a way that it is consistent, it is reproducible, and you have a good enough statistical average. Don't go with a single measurement, and just don't go with heights of peaks and assume that the numbers you are measuring is actually accurate. You can compare the anticipated actual lattice spacing versus the statistically measured value, and you can do statistical analysis and get some percentage error. And I have done this several times on different cases and examples, and most commonly when you do this kind of a manual measurement, the deviation from your real values and your expected value can range anywhere between 10 to 15% depending on how experienced you are at looking at the micrographs. But if you do this kind of a methodology where you are using this kind of lattice fringes after some Fourier filtering and taking an inverse Fourier transform, because you are orienting more or less perpendicular to the lattice direction that you want to measure, or the lattice plane that you want to measure, there is a good chance that some of the geometric errors are minimized. So this is one simple case where errors can creep up and where you end up misrepresenting data or getting values which are not really accurate. And from our experience, we've seen that people end up coming saying that there is an error, I'm not getting a match between the actual expected lattice spacings and the measured lattice spacings from TEM. And also with different magnifications, people say that, yeah, I mean, at 400,000x I get d-spacing as so and so, whereas at 600,000x I get a different d-spacing. And more or less than the change in the magnification and the field of view that you are measuring, there is a greater likelihood that errors can come up when you are actually measuring by drawing lines. So this is one simple example, and let me show you a case where you can prepare some figures for a paper or a publication using some STEM data. That is what I'll show you next. So let me open another program called ImageJ or Fiji. This is another freeware which is available and extremely powerful tool for all kinds of microscopy analysis. So ImageJ or Fiji are a Java-based program which is having a very nice user base, and there are forums where they teach you how to use different plugins to do lots of image analysis. I'll show you two examples. The first case is preparing a sort of a figure for a publication using some simple tools in ImageJ. So, for example, I have these HR stem micrographs which are like this. So here is my HR stem micrograph from strontium titanium oxide. There is some scanning error here. You see there is some lines that are there, and the reasons for this could be many. And here is a drift corrected image. And we have the corresponding EDS maps for strontium and titanium here, and they came from a slightly smaller area like this. Now, you can actually directly put one next to the other. And one common way of presenting these images would be like this. So I usually use PowerPoint to make images, and it is a simple, readily available tool. Most of us use PowerPoint for making presentations, and you can either do this in Photoshop or PowerPoint or whatever way you want to do and you're comfortable with. So let us say I have this here, and the images I had were 1, 2 and 3. Let me close this. I wonder why it pops up, but anyway. So I've seen most commonly publications where figure is shown either like this, one below the other, with the elements being added, and you can then just save as a picture. So this is one common way to show a STEM micrograph. Now you might wonder, is this actually acceptable? Well, if you're not that particular and not that concerned, people do this, but it doesn't look very elegant. So there are better ways to present this. Let us understand how. So it is important that when you're using more than one image in a panel, so here you have a larger field of view and these two are slightly smaller fields of view, and we didn't change the magnifications or anything. So having a scale bar in this particular image here and not having a scale bar here doesn't look that nice. When you're drawing comparisons, let us say you have two different conditions from which you're trying to record EDS data, and you have an image like this and you're comparing it with another image, let us say with slightly from a different region, and it is not always sure that you might actually be recording the data from the same sort of a field of view, and when you draw a comparison, a good practice is to ensure that the fields of view are more or less the same when you are comparing two different features from two different regions from a specimen. So how do we do this? You always record an image which is reasonably large in the sense, say 512 or 1024 cross 1024 pixels or something, and obtain EDS data from smaller portions there. And you can also prepare the image by first selecting a region like this, and in ImageJ there is a tool in which you can add a scale bar. So on this image on the left, we do not have a scale bar. So the way you can measure it is you can zoom in this particular region and then choose this rectangle thing that you see, and let us say I draw a square here to exactly match with this black portion here. And I know that it is 65 pixel width, and when you go to analyze here, there is something called as set scale. You can do 65 pixel is 0.5 nanometer. So when you do that, this comes from a region of 2.9 cross 2.9 nanometers. And in general, through ImageJ, you can always add a scale bar, and that is by doing this, analyze, tools, and then scale bar. You can do the following. I can give a black background and, for example, lower light or lower left, whichever makes sense for you, and then you get an image like this. So this is from the entire area, but the EDS map you had here is from actually a smaller region. So there is another image which I have just cropped a while ago. So let me just drag it here. So here we have the drift corrected base image, and from this, with the corresponding area, I accurately selected the region from where we obtained the EDS maps, and this is the region from where we obtained the EDS maps. And in this, we know that the scale bar is 65 pixel is 0.5 nanometer, and if I add a scale bar now, (65 pixel is 0.5 nanometer. I'll make it global so that all the images have the same scale bar, and analyze, scale bar. I can either indicate it with a number here, or I can also remove the number. I can just remove the text, and for now I'll just keep it, and let me call this as image 1, and this is strontium, this is So here is strontium. Here is the image 1, and here is overlay. So if I insert the pictures here now, there's one thing which I missed out is in this image, while I'm saving it, I should say image and flatten. So I should go here and then click on flatten, because when I have the scale bar as an overlay, it usually does not save the overlay if I do not flatten it. So I have the image here now, and let me replace this with the flattened overlay. And if I save this as an image, I can go here and say file, so edit, paste control, okay, and then I can paste the clipboard. I can diff, so let me call this as figure 1, for example, and even this let me so here are two images where the area from which you got the EDS is not corresponding to the micrograph, but whereas you see here from the exact same region, you have the strontium and you have the titanium maps and you have the overlay. You can also add the information such as insert a text box and then put it here. You can add strontium, and I make it in white color. And I have titanium, So I have to adjust the canvas size a little bit here. So the canvas height is 281 pixels, and then if I save this as a TIFF file, calling it figure 1, this image now looks more or less publication ready. Now let us look at how you import an image stack and do some basic operations on an image stack. So here is an image series that I have where there is growth of some kind of a secondary phase. Now in this is an in-situ movie recorded in STEM mode where a thin film was heated at around 180 degrees centigrade and beyond, and you can see that there is a growth of this secondary region, and being HADF mode, you see the heavier element, which is silver. This is from a silver copper thin film. It actually grows more brighter, and the darker ones are copper here, and there is some sort of a phase separation. Now this is from a movie which is grown and it saturates to a temperature, and you see that there is some drift here. There's a lot of variation in most of the frames here, but let us say from the last few frames, let me take, for example, 220 to 240. I just have this set of frames here now where more or less so I have this stack here where there is a slight shift. So when there is such a drift, you actually call this as a process where you want to correct the drift. You call it as registration. So ImageJ has a given plugin already. There is over here plugins and stacks. If I click stack registration, you can choose the kind of transformation that is there. Here it is a translation, and when you apply this, it kind of checks in X and Y direction how the image has shifted, and it corrects for the small changes here. If you see closer on the top, in this particular image here, there is this little black band that starts appearing, which indicates there has been some correction here. And if I crop that frame off, so let me remove the scale bar. It still has the previous configuration. So I'm not much worried about the dimension of this at this moment. So after correcting the drift, if I do Control Shift and X, I end up with this kind of a frame. So this is one sort of an operation where you're correcting for drift in the frames. This is simply called as stack registration. It comes in handy when there is only translation. And there's another interesting plugin here in ImageJ called as Analyze Particles. So typically when you have two phase regions like this and you want to know how the dimensions of one of the phases has changed over time, you might want to do the following. So in this particular image, I see there are regions where there is a significant change in the intensity at this location. It could be for various reasons. In fact, in this particular thin film, the sudden changes in thicknesses here can cause this kind of bright spot here. So possibly because we were not completely getting rid of the diffraction contrast while this image was being recorded, you get this kind of regions here. But for now, to analyze the particles in one of the frames here, I just duplicate this one and I select this. So in this particular one, there are two ways to actually analyze the particle sizes. You can directly go to the plugin here and say analyze. So let me first select the threshold layer, image, adjust threshold, and when I click on threshold, this window comes up. So there are different presets that you can choose. You can use maximum entropy, for example, or mean or minimum error. So this is something which you do visually till you see that one of the phases is completely selected. This is an HAADF image, so the background is dark. So you can choose this dark background here. If I don't choose the dark background, it selects the other phase. So either way, I can do this or do this. So let me duplicate this so that I can measure the particle sizes. So in this particular image, I know that this is from a field of view where I had 65 pixels was actually 100 nanometers. And even here. So after choosing the threshold, if I click on Analyze Particles here, it asks me how to define the particle size here. So let me say the smallest particle that I can measure here is, suppose, this one. So I can approximately measure this, and when I click Control M, it comes up with so the area here is approximately 430.769 nanometer square. So if I say analyze particles, if I give the smallest particle size is approximately 10 to infinity, I can show the overlays here or the outlines, and I do the following. It actually creates portions like this. I've just shown you a few examples of simple image operations that you do to measure the lattice spacings in HRTEM mode, and then I've just shown you a way in which an image is created just using simple tools like PowerPoint, and also something like measuring the particle sizes and so on from an image stack, and also something like stack registry operation. These are a few basic tools which you can use to actually analyze your data. So hopefully this sort of a tutorial session is somewhat useful for you to get used to the software. I've only shown you some very simple examples, and as you start using, there are more and more open source plugins with ImageJ, and there are also plugins for digital micrograph. But before you start using any plugin, I strongly advise you just look up the reference. I'm sure these plugins would have been published or used somewhere. Read about how these plugins function, and then check if it is suitable to your case, and only then use them. So with that, I'll end this particular tutorial session, and moving on, we'll look at a few applications of electron microscopy and the more recent advancements. Thank you.